Okay, we're starting. One-sided limits. Okay. So if I want to specifically ask you, guys, we're back on track now. Okay, so if I want to specifically ask you, I want you to figure out what it's approaching from the left side or from the right side. There's a special way to label that. Okay? Well, if I just wanted from the left or just wanted from the right. So if we had that weird graph, I'll draw it in here. Right, the steppy one. What's it approaching from the left or left, right? Right? It's approaching two different things. And if I asked you what is it approaching from each side? Now, the limit in general at this point doesn't exist, but I could ask you specifically a particular side. So those are called a left-hand limit and a right-hand limit. LHR and an LHO. Yeah. Okay. So the limit of L1 of f of x as x approaches a from the left is called a left-hand or left-handed limit. Left-hand limit. The left hand. So we want. I know, but it's not. It wouldn't be a show. LHO. Okay? So when you see this little negative sign, it means that you want to approach it from the left. Do we need to write that all out? No? We can. Right? That little negative there, that was a little bigger than I intended. Let's try a little one. Okay? There we go. So that little negative there means approach from the left. I'll just write that. I won't write the whole thing. Approach from left. Okay? Now, if you see that if we're going to approach it from the right, it's going to call a right-handed limit, or right-hand limit. Yeah, it could be a graph, could be an equation. Yeah, not a fun. Okay, so as long as we have this little positive here, that means approach it from the right. Just one-sided, yeah? Just for one-sided. So that little plus means from the right. Which it makes sense. Negative is left, positive is right. Just like a number line. No. Okay, so the limit is said to exist. Exist. You know what's funny? I spelled that right? Yeah. Okay, good. I used to always have trouble with the word exist. I don't know why. I don't know what I used to write. Oh, I used to put an extra S in there somewhere. Why? I don't know. So my notes online has an extra S in there. Just ignore that. Okay, so when does the limit exist? Sorry, I was distracting you. Well, only if the limit on the left-hand limit, is the same as the right-hand limit. So there's no steppy thing. Okay, that's one word to read. So if and only if the left, so I have to write this out. The limit as x approaches a from the left of our function is the same as the limit as x approaches a from the right. Okay, then we could say the limit exists. So as we approach that number, if it's approaching the same thing, then it exists on both sides. If it doesn't, there's problems. It doesn't exist. Okay, so we're going to look at the square root of x plus 3. It's often really helpful to graph, to sketch the function to solve these. So think about, to sketch this, do we all know what the graph, the square root of x looks like? Yeah? No? Right? You should know that. That's kind of expected that you know that that's the square root of x. So what transformation is happening here if we have x plus 3? 3 to the left. So we're starting at negative 3. Good. Look, transformations. It's coming in handy in calculus. Did that? Oh, that was a test. Thank goodness. Now you got it down. Okay, so that's going to really help us. Why? Well, let's look at this. From the right, as we approach -3, what are we approaching? The y value. 0. Yeah, good. From the left, can we approach the graph from the left? No, we can't. Does not exist. Okay, does not exist. Because there's nothing there. We can't approach it. So does the limit exist in this case? No, the limit does not exist. So it has to approach the same thing on both sides. So right-hand limit does not equal left-hand limit. Therefore, the limit does not exist. Okay? Okay. Okay, to solve this problem, we're going to have to review some stuff. Everyone loves absolute values. Right? They're just so cool. Because whenever, it's like a jail. Did that Mr. Trumbull ever tell you it's like a jail? He didn't? It's like a jail, right? Because the vertical bars, and it reforms you. So whether you're good or bad, when you go in, you should come out good.
But if you go in good, then it kind of makes you back and you're like, well, I shouldn't be here.
No, that's not the point, though. That's not the point of jail. Okay, so let's look at this. If it's a positive value, remember this, guys. Remember, if it's a positive value, it's just equal to a, right? We don't have to change. If it's absolute value of 2, it's just equal to 2. Okay? Now, if we have a negative value on the inside, if it's less than 0, what do we have to do to get rid of the absolute value? Multiply by -1, and that's how it outputs as the positive. Okay? So that's what we need to review. So in this case, what are my critical values here? My critical value, actually. That point where it's changing from positive to negative of this guy. 6, thank you. Thank you. Okay, so it's 6. So we're looking when x is, so when is it going to be positive? When it's above 6 or less than 6? Greater than or equal to 6. So if the function is greater than or equal to 6, do we have to change x minus 6? No. Okay. However, if it's less than 6, what do we have to do to the inside to make it positive? Multiply by a negative. Alrighty. So you remember that? Oh, where did that go? When x is less. Yeah, I think it disappeared. It's always a smart. Just less than, right? Because the 0 is included in the positive. Okay, so let's talk about this. If x approaches 6 from the right, so if you need helps with your lefts and right, just draw a little number line and go, okay, left, right. L check mark, right? You ever did that? L for left, check mark for right. I know. Okay, I just changed your life. So let's talk about, guys, sorry, it's my fault. I do this sometimes. Okay, so when it's larger than 6, it's just equal to x minus 6, right? It was positive, so we don't need the absolute values. Guys, you with me? Sorry, my own fault. Jonas? Sorry. Okay. So when it was greater than 6, right, we didn't need the absolute, we just dropped them because it's positive. If it was less than, from the left side of 6, however, it was going to be what kind of number? Negative. So in that case, it's equal to negative x minus 6. Okay? All right. So now let's approach it from the right using this that we've already used. So from the right, it's just x minus 6. From the left, we'd have to multiply by -1. So from the right-hand side, do we actually need these absolute values? No. So it's just x minus, limit. So it would be 1. limit as x approaches 6 from the right, x minus 6 over x minus 6, which equals 1. Good. Now let's look at the left-hand side. So from the left-hand side, this would be a negative value, so we'd have to multiply it by negative. So what is it approaching? Negative 1. So from one side, it's approaching positive 1. The other side, it's approaching negative 1. So what can we say about our limit? It doesn't exist. So we would just say does not exist, or DNE if you like to write that. Why? Because left-hand limit does not equal right-hand limit. Makes sense, right? Yes? Ish. Sort of. Okay, so moving on. Continuity. Or what is a continuous function? Okay, so the formal, get ready for this because it's going to be really deep. The formal definition of a continuous function, it's deep, is be able to draw it without lifting your pencil. Okay, so a continuous function is solid line with no breaks or gaps in it. It can be drawn without lifting your pen or pencil. Okay, so no breaks, no gaps, no asymptotes. It's continuous if we can just draw it without lifting our pencil. Then it's not continuous. Yeah, a circle could be continuous. But then it's not a function, you're right. So we're talking about functions. Sorry, darn. Okay. So anyways, moving on. I know this is a long day. It's a lot of stuff to take in, right? It's a long day. A function f is continuous if the limit, this is saying the limit as x approaches a is equal to the point. Okay, that's basically what it's saying is the limit equals the point. So not only do we have to approach something from both sides, but the point actually has to exist at, so it approaches the same thing from both sides, but that point also exists. Then it's continuous at that point. Okay, so what does this imply? Yeah, but it wouldn't be continuous. Yes. Okay, so 3 conditions for continuous. So f of a, so the point, is defined. Meaning there's a dot, right? There's a dot, or it's the point actually exists for it to be continuous. Okay? The limit, I'm going to draw a graph that might help. We'll call this A. We'll call this f of A. Okay? So the dot exists. That was condition 1 right there. There's a dot. Okay? Then the limit at x equals a exists. So as I approach it from the left, it's approaching the same thing from the left and the right. So then we can say it exists. And the last condition is that the limit has to equal the point. So the limit as x approaches a for our function actually equals f of a, the point. So the limit is the dot itself. So we're going to draw some pictures in a second. So if the function fails to satisfy any of these 3 conditions, it's called discontinuous. And it's not a continuous function. So all polynomials are continuous. Endpoints can never be continuous since you can't approach it from both sides. So, Yep. Okay, so let's draw 3 different conditions. So we're going to try, let's draw, satisfies 1 but not 2, number 1 but not 2. So so I'm trying to say, what did I mean by that? Satisfies 1 but not 2. Okay, so there must be a dot, but the limit doesn't exist. It's a steppy thing. Yeah. Okay, so here's an example of that first one. So the dot exists, right? The point exists at A, so we'll call this A. But does the limit exist? No. Why? It goes to different steps from both sides, approaching different things. Okay, now satisfies number 2, but not 1. So the limit exists, but there's no dot. Oh, okay, so whatever you want to draw, there should be an open circle somewhere at A. So notice, yes, the limit exists, approaches the same thing from both sides, but is there a point at A? No, it's a hole. Okay, and the last one says satisfies 1 and 2, but it's not 3. All right, not number 3. So there must be the limit exists. There's a dot that exists, but the limit doesn't equal the dot. How could we draw that? Anyone want to try it? Okay, Ben. Try and draw an example. No, so we're saying at specifically A, the dot exists and the limit exists, but the dot and the limit are not the same thing. Yeah, you want to try? No arrows. Don't have to try. The arrows, I'm just showing the limits. They're not right. Okay, do you want me to show you?
No.
It's very similar to the last graph that we just drew. What else? All we need to add is
Another dot.
Another dot.
What?
Okay, so let's talk about that. Does the point exist? Yes. Okay, so does the point exist?
Yes.
Yes. Does the limit exist?
Yes.
Yes. Does the limit equal the point?
No.
No.
Wait, so what is that point? What is it?
I don't know, some number up there. Yeah.
Like, how is it? It's like, how is it related at all?
It's a function. Passes the vertical line test. So at this A, it's up here, it jumps. So we'll look at a graphical example in a little bit. Okay. All right. Your homework, I think, has. Do I have it attached there?
Depending on how you look at it.
Okay.
Does it be in the same X?
What do you mean? Yeah, this has to be like right. Yeah. Okay, moving on. Let's look at a step function. Now, guys, what I've noticed from the past, have you guys graphed step functions before?
Yes. Oh, graph step functions?
Like something like this before? No. Okay. I'm going to teach you how, because it is something that you should learn how to do, and that's the last part, is to graph it. Okay? Yeah, we're today. I don't know. Might be in functions. Yeah? Okay. Well, they're not that hard. They just look really ugly. Okay, so in order to determine, guys, algebraically determine where the function is discontinuous, there's 3 possible breakpoints where the graphs can change, right? So it's a particular function when it's less than 0. When it's equal to 0 and less than 3, it's equal to 1. The y equals 1, so horizontal line. And then the graph is 4 minus x, so a vertical line, like a linear equation, when x is greater or equal to 3. So it's basically 3 different functions working together. So when we sketch it, it's going to look something, just to give you an idea what we're graphing here, it's going to look something like this. Let me just show you. We're going to graph it ourselves. And then, okay, it's going to look something like this. So to give you an idea what's happening, it might be easier to, the reason why, let's think about this, okay? When it's less than 0, it's the equation y equals x squared minus 2. When it's less than 0.
Oh.
Okay? When it's between 0 and 3, it's the equation y equals 1. Okay? And then when it's greater than 3, it's the equation y equals 4 minus x. That's what a step function is. Okay? What?
Sorry, when it says y equals 4 minus x.
That's the equation when x is greater than 3. Well, I'm just wanting to give you a visual picture, okay, of what the graph looks like at this point. So just a rough sketch, just a very rough sketch. So we're going to end up sketching this properly in a moment. We get later on in the question, but I wanted to give you, so really what happens is at these values is where we have a possibility, is where it can possibly become discontinuous because the function is changing and it could be jumping to something else. So those are the places where we need to check whether it's continuous or not. So we have to check those 3 conditions. Okay, guys, you with us? Okay, so A, algebraically. So if you look at the function, if this is f of x, there's 2 possible places where it's changing, right? So we have, when it's less than 0, it's the equation x squared minus 2. Then from 0 to 3, it's y equals 1. And then 4 minus x. Okay, those are the equations for the graphs between those parts. So we can illustrate it a little bit on a one-dimensional line to see how it's changing. The only places we have to check for continuity, continuousness, right? Continuity are the breakpoints. So in this case, it's at x equals 0 and 3. And so for each one of these, we have to check if those conditions are satisfied. So those are our breakpoints, 0 and 3. We see them up here. That's where the function's changing. Okay? Okay, so we have to do, for each one, we have 3 conditions to check. So we'll start with x equals 0. Okay, condition 1, what's condition 1? Okay, go back to your notes. There has to be a dot. The dot exists. So we want to check what is f of 0. So at 0, which equation is the graph? Which one of these? First, second, or third? The second, right? Because that's where it has the equal to 0. So what's y equal to at that point? Always, yeah? Yeah. But so it only, well, yeah, open 0 for this part. We're not drawing it though, this part. Oh, no, don't worry about that right now because we're not actually drawing it yet. I just want to show where the breakpoints are because one would be open, one would be closed. Okay, what's the second condition? So does the point exist? Yes, the point exists. Okay, what's the second? Does the limit exist? Okay, so here, I'm going to write this out. The point exists. Does the point exist? We know it exists because I can plug in 0. It will give me a y value. Yeah, it's 1. Okay. So second, the limit. Does the limit exist? So we're going to check that. So we have to approach it from both sides. So we need to find the limit as x approaches 0 for our function from the left and from the right. So we're going to do the left first, if that's okay, for our function. So this is where this one-dimensional line can be helpful. So on the left side, I'm going to plug in this equation. What, 0 squared minus 2? Negative 2. And I already kind of roughly sketched. Notice from the left, it's approaching negative 2. Okay? Now we do from the right. So from the right, which equation will I use? Y equals the right of 0, 1. And that would just equal 1. So does the left-hand limit equal the right-hand limit? No. So right away, we don't have to check condition 3. We can stop and we can say what? The left-hand limit does not equal right-hand limit. Therefore, x is continuous or discontinuous? S is discontinuous at 0. Okay? Now we have to check the other one. It's fun. No, we technically haven't drawn the graph yet. No, I just roughly sketched it for you, just to give you a picture in your mind of what's happening. But you do it on an exam. You're gonna have to do this on your unit exam. All 3 steps. This is gonna be on there, guaranteed. Written response. It will be there. Start this on your page. Guaranteed. Okay. So number 1, what's the first condition? You need to know these. Does the point exist? So f of 3, what would that equal? So we go back here. So which equation will we be using? First, second, or bottom? So we go 4 minus 3, which is 1. Good. Number 2, what are we checking? Does the limit exist? So how do we have to figure the limit from x approaches 3 from first the left-hand side. So from the left-hand side, go back to our little number line. We're going to approach 1. From the right-hand side, plug in 4 minus 3, and it approaches 1. So what can we say about the limit as x approaches 3? Equals, if it approaches 1 from one side and 1 from the other, it's approaching 1. Right? So that's what it's approaching. So it's approaching 1. So the limit exists. It actually is approaching 1. And last, what's the third condition? Does the limit equal the point? Yeah, the limit as x approaches 3 of f of x equals f of 3. The limit equals a point. So therefore, what can we say? Yeah, the function is continuous x equals 3. So the only place it's discontinuous is x equals 0. Okay? And last, it wants us to sketch the function. Ooh. How are you all feeling? Lots. Yeah, it's a long day. Okay, we're almost done. So let's properly sketch this together. I'm going to show you how. Okay, so hopefully you have some room on there at the bottom of your page. Okay, so listen up, because I don't want a lot of you asking questions later because you weren't listening. And I know it's the end of the day, and I know you're tired. Okay. What? Okay. So I'm just going to help you sketch this. Okay? So how do I get that graph that I sketched over there? So we're going to draw our line. Okay? So obviously our important points are 0 and 3, but we need to actually have some idea. So what we're going to do is we're going to start at 0 or at less than 0. So we want a couple points. So maybe you'll start at -2. -2, which function are we using? The first one, yeah. So let's plug in some values. So -2 squared minus 2 is 2. So 1, 2. So -2 is 2. Okay, you can also use your knowledge of transformations a little bit, right? Okay, and then I'll plug -1 in. -1 squared minus 2, -1, and then 0. Now, is it equal to 0? No, so we're going to have an open circle, but we still want to draw it because it's going to 0. So 0 squared minus 2 equals -2. So that's going to be open. Now we know this is a quadratic, an x squared, so we're going to sketch it as such. Okay, so you're actually plugging in values. Now we go to the next function. So this one's pretty easy. At 0, what does it equal? 1. And it actually is filled in there because that's where the equal to symbol is. At all the way to 3, it's always going to be 1. And then at 3, what do we have to do? Open circle because we don't have an equal to symbol there. So now we go to the next equation. Plug in 3. 4 minus 3 is 1. So what's going to happen now? Fill it in. So I plug in another one, 4. So 4 minus 4 give you 0. 4 minus 5, negative 1. It's a linear graph, right? Yeah, it's like the graph I drew over there. Okay, so we just, right, you can't use your graphing calculator on a test because you won't have one. You have to be able to plug in values and create the graph. Okay, we made it. You survived to the end of this lesson. So there's 2 quizzes on Monday, unless you want them tomorrow.